Good afternoon. So we are now ready for NETA questions, September the 15th, 2020. So today I'd like to spend some time dealing with the National Electric Code, Article 250, which is grounding and bonding. So I had a couple of questions to ask, and then we're going to go over some highlights of that section of the National Electric Code. So question number one. Please name 6 types of electrodes permitted for grounding, according to Article 250 of the National Electric Code. So let me look at this and find my, it's like, so I can have a metal underground water pipe. Just as a side note, it doesn't really good to have a metal underground water pipe. If you've got PVC inside the house that meets up with that, that's a problem. You can have metal in-ground support structures. You can have concrete encased electrodes. I can have a ground ring. I can have rod and pipe electrodes. And I can have plate electrodes. So all of those items can be found in Article 250.52, if you want to look at that. So question number 2, what's the acceptable resistance to earth value for commercial industrial systems that would not require supplemental electrodes? In other words, these would pass the National Electric Code inspector, and I wouldn't have to have additional support or additional electrodes driven to the ground to try to take care of that. And that would be 25 ohms. If you're looking for that, that would be found in Article 250.53, Section A, Section 2. What are the spacing requirements for supplemental electrodes if required? Good NETA question. So if my ground resistance test indicates that I need to have additional support electrodes, they have to be not less than 6 feet apart. So basically that means greater than or equal to 6 feet. And that's in Article 250.53, Section A as well. That's A3, if you're interested in that. So those are some typical type questions that you might get asked on Article 250. So I thought I might spend a little time talking about the National Electric Code, Article 250. So if we talk about the severity of electrical shock, that's what we're trying to prevent here. We've got 3 elements. We've got the amount of current that's going there, the length of time that the current is present in the body, and the path of the current that flows through the body. Obviously, going across your chest, across your heart muscle is a concern. The amount of current's always a concern for danger, but the length of time. So typically for us, in a substation generating plant type setting, we're thinking like 15 cycles or a quarter of a second. For all industrial settings, we're probably talking about 30 cycles for the fault itself. But if we have ground fault systems that are not properly installed, it may not trip at all. So looking at the diagram of that, or looking at the history of that, we can understand that 3 milliamps of current, 3 thousandths of an amp that we can feel, somewhere between 7 and 10 milliamps, 10 thousandths of an amp, I can no longer let go, 30 milliamps worth of current, and I can have real problems in trying to breathe and catch my breath. Somewhere between 80 and 100 milliamps, my heart can stop. And basically, 5 minutes after that, I'm gone. So the amount of current doesn't take a lot. If it's there, crosses across the heart, and is there for any length of time. So if I look at series and parallel paths for current, the thing that we need to understand that is current will always return to the source. No questions about it. It's got to get back to the source that provided that current to start with, okay? And current will return to that source in as many different paths that's available to it. So it'll take every chance, every opportunity. It may be one path that's less resistance that most of the current will flow in, but it will return back to the source, and it will take every available option to it. Now, the amount of current on a particular path depends on the impedance or the resistance in ohms of that path. So the higher the resistance, the less current is going to go through that section. So that's a precursor for what we're going to talk about when we start talking about this National Electric Code, Article 250, for grounding. So here's a breakdown of grounding and bonding. So if we look at Article 250, there are several sections. We have the general section that we're going to talk about today. There's the system grounding section. Down here, there's a grounding electrode system that we get involved with quite a bit with follow potential and point-to-point testing. Talks about raceway, grounding equipment and grounding conductors, methods of grounding electrical equipment. There's a section on bonding that applies to all of these. And then we have a section on direct current systems that we don't get involved with, and a section on grounding systems and circuits over 1,000 volts that most people don't get involved with, but yet we may get involved with that quite a bit. So part one, general. So when we talk about the general section of Article 250, it talks about what systems and what equipment are required to be grounded. You see, everything is not required, but it's very specific on those items that are required. Then we talk about the circuit conductor to be grounded on grounded systems. So for instance, a neutral on our house, that's a circuit conductor. That carries current, but it's to be grounded at certain locations. We'll talk about that. We talk about the location of grounding connections, where they are. It talks about the types of electrodes and the sizes of grounding and bonding conductors. General part one talks about the methods of grounding and bonding. And it also talks about the conditions under which guards or isolation or insulation could be utilized in situations where systems aren't grounded. So grounded or insulated, those are the two choices. So some definitions. The bonding jumper, supply side. It's a conductor installed on the supply side of a service or within a service equipment enclosure for a separately derived system that ensures the required electrical conductivity between metal parts required to be electrically connected. Boy, that's a mouthful. So some of you have listened to some of my classes before. But I can remember when I was young, first starting out at Indianapolis Power and Light Company, and I made a trip in the field with one of our senior field reps that was meeting with a customer and an electrical contractor to talk about service to a new facility. And the new facility was a house, had a 100 amp service on it. But I noticed some things in that circuit. Now, it was and we're talking back 1971 here. So it was a new system. So I had hot coming in, and I had hot coming in, and I had neutral coming in. And on this side of the guy's circuit breaker panel, all the white wires. And on this side of the guy's circuit break panel, all the bare or green wires. And I saw that this went to ground rod. Sorry about that. Went to ground. Right there was the ground rod. But I also noticed that there was a jumper from right here that went over to right there. So this white, the neutral connection, was tied to this ground, the bare wires, okay? So when we got back in the office, Ted Miller, my mentor back at the time, says, "What did you learn today?" And so what I told him is like, what I learned today was neutral is equal to ground. And that caused him to go red-faced because he was a scholar in the National Electric Code. And he told me to go back home at night and to read Article 250 on bonding and grounding, okay? And I came back the next day after I read it, and I still said, "Ted, I don't know, but I just know this. There was white wires were connected to the bare wires, and right where I saw it, neutral is equal to ground," okay? So we'll discuss that in just a little bit. But what I found out after he got to the point where he could talk to me, that this was a bonding jumper. So that bonding jumper was at the service equipment. There it is. At the enclosure for a separately derived system, separately derived because out on the pole there was a transformer. And no, there's no electrical connection from one side of the transformer to the other. So this secondary, the 120, 240 volt single phase house service was a separately derived system. Completely different electrical system than what the primary side of that transformer was. So that was a little hard for me to grasp at the time, but I understand it now. So going forward, I look at that service entrance situation. So here's my kWh meter that we all have on our house, or the customer has. There are my two hot wires, 240 volts coming in. There's my neutral coming in. And going from this main disconnect here, main circuit breaker, I see that they're all leaving, going to the rest of the house or all my other loads. But I'll make a very quick notice that look right here. Neutral and ground are tied together right there. But that is at the service entrance, okay? This number 4, AWG, size of the cable, supply side bonding jumper. So that is where it's connected together, where I connect ground to the neutral. And that's the only location in the world that I can have those two things tied together. So if I look at this separately derived system in detail, that's what I've got right here. I can see that I've got the separately derived system. There's my transformer, separately derived. There's my hot leg. Here's my other hot leg. And hopefully you knew this, but the center point, the center tap of that transformer is where I have my neutral, okay? So here's 120 volts, here's 120 volts, and across the whole pair, there's my 240. So there's my incoming. I see my neutral coming in here. It goes right there. And notice, it goes to ground, okay? So the neutral connection on the secondary sides of this transformer, the supply side of this transformer, goes directly to ground, okay? It's there. And guess what? Back at the source, eventually, it's connected back to the ground on that case of the transformer, okay? So every enclosure is tied together there. Now, if I look down here at the load, There's my load. Again, there's my system bonding jumper right there, the little connection from the neutral to ground. But if I look at my load, there is no connection in my load. There's hot one side, hot the other side, 240 volts. There's no path to ground from the load, okay? Now, there is a neutral here, or not a neutral. There is a ground connection here. The case of all electrical cabinets are tied to ground, but there's no path for current, neutral current, to flow back. If this was a light bulb and there was just 120 volt source there, again, there would be no connection to ground there. Now, the actual case of that light can be tied to ground right here, because I don't want to be able to touch that case and have a tingle on my hand. So that's the way we approach a separately derived system. Now, the Article 100 in Section 250 talks about the grounded conductor, okay? So this is a system in which, or a circuit, it's a circuit conductor. It is a current carrying conductor that is intentionally grounded. So if I look at these systems, a three-phase, four-wire system, a Y system, I've got the neutral point right there. Guess what? It's intentionally grounded, okay? I'm not showing the primary of the transformer. If I look at the single-phase, three-wire system, by definition, right here's the neutral conductor there. It's grounded. And if I look over here at a delta three-phase, four-wire system, where I have maybe 120 here, 120 here, 240 here, 240 here, I wouldn't go from neutral to this side. That's the high leg, the X2 is. But I do have a ground. This is my neutral for my 120 volt lighting inside that facility, and it goes to ground. So a grounded conductor, that's a system or circuit conductor that is intentionally grounded. For these systems, it also is the neutral conductor in every example that I've shown there. So understand the difference between a grounding conductor and a grounded conductor. The grounding conductor is the actual conductor going to ground. Okay, section 250.4, general requirements. There are some general requirements on grounded systems. Electrical systems that are grounded, they've got to be connected to earth, solidly connected in earth in such a manner that will limit the imposed voltage by lightning or line surges or unintentional contact with a higher voltage, and that will stabilize the voltage to earth during normal operation. So I want to have a solid location for ground path for current to flow, and it has to be solidly grounded there as per 250.4. Now, in that same section, 250.4, grounding of electrical equipment. Normally, non-current carrying conductors, materials, enclosures, they shall be part of such equipment. They need to be connected to earth as to limit the voltage to ground on these materials. So can't be a situation where you come up and touch an electrical box and be shocked there. It's got to go to ground, okay? In the old days when we had two-wire electrical systems and no ground going to the washer, a lot of times we had washers or dryers, gas dryers, where you could actually touch the case of the washer or the dryer and get a little tingle there. That was because it was not effectively grounded. Now, this bonding of electrical equipment, normally non-current carrying conductive materials shall form, conductors or equipment or forming part of such equipment shall be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. So this is separate from the neutral, but all of my cases, all of my light fixture boxes, all of my electrical cabinets have to be tied together, returning back to that lone ground connection back at the source. So they're going to be tied together. They're bonded together. Effectively, I want an effective ground fault path. So it's got to be capable of carrying the maximum ground fault current that's going to be imposed from time to time on any point in the wiring system if a ground fault occurs. So some consideration needs to be taken into the fact of how much ground fault can actually occur there. So let's look at an effective ground fault path. So we're back to our separately derived system here. There's my source, okay? Got my meter, got my main, got my panel. And if you'll notice that in this situation, my main supply panel is tied to earth right here, okay? Now I also know that the transformer is tied to earth back on the pole. And I see a light orange line here. They're both going to ground. So I can have some ground current flowing there. But what I'm worried about is from here on back. Okay, so here's my main bonding jumper where neutral goes to ground. Okay, right here at this location. There's my neutral, there's my neutral, there's my neutral back at the transformer. It's tied to the transformer. That transformer may be 200 feet away. So I have to have the effective ground at my service entrance equipment, my main right here. Some utilities want you to have that in your main disconnect circuit breaker panel. Some utilities do that themselves inside the meter cabinet. That's up to the local jurisdiction. But the situation here is like all of a sudden I have a ground fault over here. Now, where's the current going to flow? I have to have an effective path. It's going to go here to the case. It's going to go through that ground wire that's connected to the outlet, which goes to the next case, all the way along the way. Not one time until it got to this location did it have an option to whether it wants to go back on the neutral or the ground. This is the only place it can get back on the neutral of the system. So everything from this point forward or to the load is making sure that all ground fault current goes through that grounding conductor. So electrical system grounding. I want to make sure that I can limit high voltage imposed in the system from induced lightning or line surges. So the worst case scenario for a voltage surge typically is that lightning strike that we see here. So I've got the lightning strike that hits the power line. I've got to effectively get that to ground, and I do not want it inside my house. I want it right here straight to ground because I want to limit that voltage and clamp it right there. So that's my electrical system path that I have. So looking here, the note is that the system grounding stabilizes the system voltage, okay? Reduces the damage from transient over voltage equipment. So it could be a lightning strike, a line gets into something else, all those sorts of things. But here's my panel. Here's my transformer. It's solidly grounded right there. Okay, so if it comes in this way, I want the current to flow and I want it to go to this ground, okay? I've got to keep it there. But notice again, even here's my disconnect. My disconnect is not connected to ground right there. That's a separately derived system. It's only connected to ground right here at the transformer in this location. So this would be like an industrial setting where I'm inside. So let's talk briefly about ungrounded systems. There are ungrounded systems, three-phase, three-wire, 240 volt, three-phase, three-wire, 480 volt delta-based systems using basically for motor type loads, okay? So that would be the basic reason for those things. And so I have the three phases here connected delta. I've got distributed capacitance. Those are not capacitors. That's just distributed capacitance on the cable. But you see, the case of the motor is grounded, but there are no grounds on any of the conductors here. So that's completely floating. But if I see here again, I get the situation where, you know what? I can carry that ground wire from the case where I started at to the case right here. And I make sure that I've got a grounding electrode. All electrical compartments are grounded, just the actual load could be isolated. So let's look at some objectionable current. So we'll look at a couple of examples where there are violations. So here's the top one. We've got a light here, incandescent light, 120 volts, I assume. But if I notice right here in its neutral bus, I've got a connection to ground right there. And I've got a connection to ground back here at my service. So this ground current has a choice. It can go back on the neutral, or, then the simple load current can go back on the neutral, or it can go back on the ground. This is not supposed to be a current carrying conductor. The neutral itself is a current carrying conductor. And I can see that neutral case connection on the load side of service equipment. I see that little connection right there where the neutral is connected to ground. That needs to be removed on this panel board because I've already got it connected at the service entrance. Objectionable current, dangerous touch voltage. So here's the situation I get into if I don't have a good solid ground. It doesn't necessarily reduce dangerous touch potential. So I can have a 120 volt ground fault right here. Okay, I can have that right there. I can have 0 volts from this pole to the ground that it's attached to right here. So Mr. J right there, he feels pretty good because he's checked it for 0 volts. But look where his knee is. His knee's right here. That ground path has to provide current flowing back to the source. And so there's going to be some voltage drop between this location and where his knee is. Looks in this case, it's example 90 volts, which means there's 90 volts from here to his knee, okay? So in this particular case, shell 1 was 82 volts, shell 2 was 90 volts, shell 3, 5 feet out was 103 volts. So without that ground going back to the actual ground of the service entrance, I can have some dangerous step potential voltage increases here. So this ground needs to go back solidly to the service entrance panel, to that ground location, so I have a direct path. Anything that's going through the earth can mean a potential hazard for me. There are certain types of connectors that are used. Section 8 of 250 talks about those. There are listed pressure connectors, there are terminal bars, there are grounding and bonding pressure connectors, exothermic welding process, CAD weld, machine screw fasteners with certain criteria to them, thread forming machine screws that could, like the ones you see in the electrical box that you're putting in your wall for a light fixture. So those are possible methods. Notice that solder is not a possible method for a ground and bonding equipment. So the pressure type equipment that we can see can be my split bolt. Okay, so I've got a split bolt there I can use. I split bolt right there. I can have a compression fitting. And I can have a wedge clamp. All of those are pressure type connectors. All of those are acceptable, if listed, for grounding and bonding. So if I look at the various connectors, I can see things. One of the big suppliers is Burndy, obviously. But I can see the various products. I can see, again, those compression fittings, all those are compression fittings. I can see bus bars that I would see on the back of possibly relay panels. So that would be a place for me to connect my grounds to. I can see a high tap connector here. Again, that's a crimp type connector. I can see the exothermic bonding, which is the CAD weld. Brad Moore and the construction group does a lot of CAD welding. Don't need any outside power, which is not much a concern anymore with the advent of battery-powered compression tools. but used to have some utility power, some source of power there to do some work, but now it's not required. I can have lug-on bus bar connections, so I can actually land my own ground bus, again, separately from everything else. I can have lugs screwed to it, again, compression. I can list separately there. So there are lots of different types of clamps. There's another different type of compression clamp used for that bus bar. And then I have a C-type ground clamp that I can utilize, which would go around the ground rod or the water pipe, those sorts of things that I can do that. I can install a ground link type connector. We've already seen some of these. And just to look at some of the different connections that we can have on the various connectors, this is showing the actual connection to the ground rod itself. But I can see here's my exothermic CAD weld right there. I have a compression connector right there on my ground rod. And then here's my mechanical connector that most of us have on our houses for the grounding. So hopefully this has been beneficial to you to go over some of the various types of grounding techniques and going over Article 250. So I think you have a better idea of what's going on there. So hopefully that'll help you on some questions regarding Article 250 on the exam. Again, you'll be seeing this on YouTube, and I'll be sending out more in the future. Thank you very much.